In this next section, which is about weak bases, we're going to employ pretty much the same strategies, except we'll be dealing with substances that accept hydrogens, not donate them. The most common base that they use in the weak base type of problems is NH3. Notice that when it accepts a hydrogen from this water, it becomes ammonium, the NH4, and left behind are hydroxide ions. And that, of course, is the definition of a base. It's reacting with water to produce hydroxide ions. Now, the textbook and the next slide were at somewhat odds to each other. So when you take a look at the textbook, you might see that first expression written as B with an H+. But basically, you can have a Kb expression where the original base, which is this concentration down here on the bottom, would be divided into the product of the conjugate acid of that base. Remember, here's the base having accepted a hydrogen times the hydroxide ion, that concentration that inevitably forms. So it's done exactly the same way. And of course, water is emitted from that expression. Now, if you can take a moment, I want you to just scan down and look at the Lewis structure column and see what all of these bases have in common with each other. And if you look at their conjugate acid in the next column, perhaps you can see where the hydrogen might be attaching. And I'm hoping that at this point you can see that all of these substances in this base column have somebody, frequently nitrogen, but it doesn't have to be. It could be like a sulfur here, that has unshared or unbonded pairs of electrons. And it is at that site that the hydrogen will be attaching. So for example, back to our ammonia, NH3 becomes NH4, and the hydrogen will attach right here to make the ammonium ion. And of course, weak bases can be ranked relative to each other. Remember, you can't have a Kb for a strong base, only for the weaker bases. And the larger the coefficient, the larger the power of 10, the weaker the base, because they're negative exponents. So in this column, it looks to me like the strongest of these weak bases is methylamine. Okay, now let's do an example problem. This is actually sample exercise 16.15, I think, but it's slightly different, and we'll show both problems here, what's embedded in the PowerPoint and what's in the textbook. So here's a 0.15 molar solution of ammonia. We draw the expression, or write the equation, and we write the expression. And notice that we have ammonium and hydroxide are the products. Ammonia is the original reactant. And this is one you use a lot also. What a coincidence. 1.8 times 10 to the negative 5 is the Kb. Now they want pH, but we'll probably end up going to get POH and then finally solve for pH. So I set up an ice chart. And initially we have 0.15 molar in the NH3, and no ammonium or hydroxide ions have formed yet. However much forms, we'll tabulate or call as X. And because it was a times 10 to the negative 5 Kb, it will be okay to omit X from the expression. We substitute in our Kb value, and it's X squared over 0.15. Very quickly you'll become adept at these, and you'll take the square root of X to find that the concentration of hydroxide is 1.6 times 10 to the minus 3 molar. Now, if that's where they wanted you to stop, great. But what they want you to do is to take that and turn it into a K or POH, and then you can turn that into a pH. Remember, there are a couple of ways to do that. I like this way. I take the negative log of the hydroxide ion concentration, and then I like the simple method of subtracting 2 from 14 to find the pH. So Kb problems are just like Ka problems, and you see more often Ka problems than Kbs, but the process is the same. This was sample exercise 16.15, and in fact, the PowerPoint version of the problem took us all the way to pH. This problem just takes you to the concentration of the hydroxide. I did want to point out that they went ahead and substituted in that concentration of the hydroxide versus the original NH3 and came up with a 1% value. So if we were having to check to make sure that ignoring the X was okay, we are okay here. If it's less than 5% of the original concentration, it's fine to omit the X and simplify your calculations. Now this one's a little bit different, and we'll talk about salts later on in the chapter. But if one is given the pH, you can actually calculate the concentration of a salt. So here's the salt, and that's a little ahead of the game, but if you put sodium hypochlorite into water, then you're going to see the pH change. And the ClO minus ion can act as a base, and so it will be accepting hydrogens, and it's probably got a Kb. We're given a 10.5 pH, and don't worry about the 2-liter solution yet, and don't worry about the number of moles yet. Let's focus on getting the Kb for the ClO minus. You always get to ignore sodium because it acts as a spectator ion, and the expression I would have drawn is down here. The hypochlorite ion can accept a hydrogen from the water you've dumped it into, turning into hypochlorous acid, I believe, and hydroxide. And now we can take the remaining, or the final pH of 10.5 and go backwards, finding the 10 to the negative 3.5. Whoops, that doesn't look right. Here we go. If I take 14 minus the pH, I will have the POH, and if I want to go from POH into hydroxide ion, that's where the 10 to the negative 3.5 comes from. So apparently the hydroxide ion concentration is 3.2 times 10 to the negative 4. That's at the end. That's when it's reached equilibrium. So that's why you see the 3.2 times 10 to the negative 4 here and there, because there was no hypochlorous acid to begin with, nor was there any hydroxide, and they both must have increased by that amount. Subsequently then, the original hypochlorite ion must have decreased by the same amount, hence they're showing X minus 3.2 times 10 to the negative 4. Now let's go back and see what they want me to do. They want me to calculate the number of moles of that salt with the hypochlorite ion that must have been added to this water, and we won't forget that they've made it a 1 level of difficulty higher. They gave me a 2-liter solution. So I've written an expression for what you see down here, and that's something you would always get points for in the AP exam, at least setting up the table, writing the equation, showing the expression. We have the hypochlorous acid and the hydroxide ion concentration, so that's why it's squared. And notice that this time, the original amount minus the change, I get to leave the X in. And the cool part is because that's not being squared. And I need to solve for X. I need to find out what was that original concentration of the salt, the NaClO, before it started to react with the water and make it more acidic. So, and also producing hydroxide ions. So what we're saying here is that if you have a problem like this, where the X is not being squared, just leave it in the expression. It's the only X that you need to solve for. And by doing some algebra, you can find that the concentration is equal to 0.31. So now we know that that solution was 0.31 molar in NaClO. And the problem that you have is that was 0.31 molar in 2 liters. So to make it 0.31 molar at the end, they must have added 0.62 moles of sodium hypochlorite. Now they didn't really show the work there, but essentially if this final concentration is 0.31, then you would have had to have double the concentration, 0.62 moles, added to 2 liters to make it 0.31 molar in 1 liter. Okay, so that's how you can use pH to determine the concentration of a salt. You generally won't see that problem too often. At the next point Vodcast, we'll be talking about the relationship between Ka and Kb, so I will end this Vodcast now.